Hey y'all, welcome back. On tonight's homework, we're looking at exponential growth and decay. Number 1 says, does this table represent exponential growth or decay? And we can see because we have a multiplying factor of 2, or we're multiplying by 2 at every step of x, this is going to be exponential growth. So to write the equation is always going to be in this form, y equals a times b to the x. And so we can see that our initial value here, our y-intercept is 5. That's going to be our a value. So y equals 5 times our multiplier, which in this case is 2 to the power of x. Number 2, we can see that the values of y are decreasing, so we have exponential decay. We'll write the equation in the same way, we just need to figure out what are we actually multiplying by. So my y-intercept is 64, that's my initial value. My multiplier here, you can see that for each step of x, I'm dividing by 4. So that's the same thing as multiplying by 1/4. So I should have y equals 64 times 1/4 to the power of x. And this is actually an exponent. It doesn't really look like that. Here, that looks a little better. Number 3, we can see that we're multiplying by something, but it's not really clear. What we do know is that it's exponential growth because it is getting bigger. And so we need to first figure out what that y-intercept is. So we do need to figure out both the y-intercept and the multiplying, the number that we're multiplying. So if we do work backwards, we can do 51 divided by 7 to figure out what that growth factor is. It doesn't come out to be a nice number. So if we're going to multiply 17 by something and get 51, I believe we're just going to have to multiply by, well, 51 over 17. Does that reduce at all? Let me double check that. 51 over 17. Yeah, hang on. That's a multiplier of 3. I thought maybe we would have to. I thought maybe we would have to come up with some fraction here, but yeah, no, this is just 3. We can see that we're multiplying by 3. Get from 17 to 51, and I figured that out by just dividing. I did 51 over 17 and found out that that is just 3. So our multiplier is 3, and what that means is we can divide by 3, work backwards in this table one little step to figure out what y is when x is 0. So we can do 17 divided by 3. Now that will not divide nicely. So 17/3 is just going to be our y-intercept. So 17/3 times 3 to the power of x. For number 4, we can see that the numbers are going up, so this is going to be our third exponential growth problem. Our multiplier here is a little bit more obvious. We're just multiplying by 4 times 4 times 4. If we work backwards to figure out what this is when x is 0, we can just divide by 4. So 2 divided by 4 is going to be 1/2. So we get y equals 1/2 times 4 to the power of x. I'm going to put this 17/3 over here just so I remember that that's how I got this number right here. Okay, let's move right along here. Number 5 says annual sales for a clothing store are $270,000 and are increasing at a rate of 7% per year. So we're still going to use this a times b to the x template, but for exponential growth, we're going to rewrite this b as 1 plus the rate. It's going to just help us figure out what that b value is. So in this case, this is really going to break it down for us. It says first, what is A? And A in this case is the $270,000. What is the R, or the rate of growth? We can see that's 7%. So I'm going to write that as a decimal, 0.07. Then what's the 1 plus R? Basically what we're doing here is we're just really figuring out what all these pieces need to be to write the equation. So 1 plus R is just going to be 1 plus this. So that's just 1.07. That's our growth factor. So now we can write the equation. Y equals 270,000 times 1.07 to the x power. For part E, it says find the annual sales after 3 years. So we just need to substitute in 3 for x. So we're going to put a little 3 right here and use a calculator to compute this. No reason to do this by hand. So I've got 270,000 times 1.07 to the power of 3. And so this is the annual sales here after 3 years is going to be a total of, why doesn't it let me do a dollar sign? That's kind of weird. I'll add it at the end here. So $330,761.61. All right, and this little formula over here is how we actually got that number. Number 6 says the population of a school is 800 and is decreasing at a rate of 2% per year. So this is going to be an exponential growth equation. It's going to be very similar to this growth equation. I'm sorry, I think I misspoke. This is going to be an exponential decay equation. So instead of being 1 plus r, it needs to be 1 minus r. The initial amount here, which is what it asks for first, is going to be 800. That's the initial population. The r, or the rate of decay, is 2%, so we'll write that as 0.02. If we do 1 minus 0.02, or 100% minus 2%, that'd be 98%. So our 1 minus r is going to be 0.98. And so now we can write our equation. Y equals 800, right? That was our A value right here, times 1 minus R, 0.98 to the power of x. So to find the population for 4 years, we're going to substitute 4, sorry, we're going to substitute 4 in for x. So once again, this is something you probably just want to put in the calculator. And since we're talking about population, we want to round it to the nearest whole number. We do not want to talk about, like, 2/10 of a person or something like that. No, there's not going to be any decimals in our answer. We are going to round. So 800 times 0.98 to the power of 4 gives me approximately 730, I'm going to round up here, 738 people. Number 7, Ray purchased a used car for $8,000. Each year it depreciates by 8% in value. So after 0 years, he first purchases the car. It's going to be $8,000. Then it depreciates by 8% in value. So we need to find what is 92% of this so that we can subtract the 8%. So what I'm going to do is multiply 8,000 by 92%. Okay, so this is going to be 8,000 times 92%. So it's depreciating by 8%. This is 1 minus 0.08. And that gives me $7,360. And then I'm going to multiply that by 0.92 again. So to get this one, I get 7,360 times 0.92. Now we start getting some decimals here, so we're going to have some change. So we have 6,771.20. Then we're going to take that number and do the same thing. We're basically going to keep multiplying this by 92% because it's going to depreciate by 8% every year. So just to clean this up a little bit. And now you can hopefully see why we use exponents for these kind of functions, because we're just multiplying by 0.92 over and over again. And it would be easier in general just to raise it to the power that would be equivalent to how many times that we're depreciating. In other words, to figure this out, we could just do 8,000 times 0.92 to the third. At any rate, we get $6,229, and I'm going to have to round, oh, it looks like down here because it's 0.504, so we'll just say 50 cents. Now I'm going to multiply that value again by 0.92. I'll actually use the full number here so that I don't have any trouble with rounding towards the end. At the fourth year, we're going to have 5,731 and rounding to 14 cents. To get that fifth year, I'm going to multiply the number by 0.92 again. And just as a reminder, I'm using that full value for number 4, the unrounded one, so that I can improve the accuracy of my final answer here. So after 5 years, the car is only worth $5,272 and rounded to 65 cents. It's a good illustration of how the value of your car depreciates and why a car is a liability and not an asset. I mean, I suppose some cars could be assets in the sense that if it's, like a classic or something that's going to appreciate in value. But most cars, the vast majority of cars, do depreciate in value. So now we can go ahead and write our equation. Recall that the way we're setting this up is going to be a times 1 minus the rate raised to the x power, where a is the initial value, in this case $8,000. The rate is 8%. We're depreciating by 8%, so 1 minus 0.08 is going to be 0.92. That's why we're multiplying by that 0.92 on every single step, raised to the x power. And so here, instead of kind of going month by or year by year here, we're just going to substitute in 10 into x to find the value after 10 years. It'll just be a little faster to do it that way. So 8,000 times 0.92 to the power of 10 is going to be 3,475. Now what's going on here? 3,475 and round to 11 cents. Okay, and off to the side, maybe I'll show you how I got that. I just took this equation and substituted 10 in here. And that's how I came up with this number. Number 8 says the table below represents the number of bacteria recorded in the daily lab experiment, recorded daily in a lab experiment. And we can see that the number of bacteria are decreasing, so we've got exponential decay. We want to write an equation for this, so we need to figure out what's being multiplied here. So to figure out that b value, what we can do is divide one of these entries, like 140,800, by the previous entry. And if this is, a true exponential function, then we should get the same b value no matter which two of these adjacent values that we pick. So I usually just start with the first few, but you could pick really any of these. Like you could do 95,951 divided by 109,036, and you should get the same b value here. I'm going to put this in the calculator. 140,800 divided by 160,000 is 0.88. Okay, so that means that it's decreasing at a rate of 12%, because 100 minus 12 would be 88. And now we can use this function to figure out how many bacteria will be left after 8 days. So we'll just substitute in 8 for x. And we should get our answer here. So let's see, 160,000 times 88%, do that 8 times, And so we get approximately 57,450. I'll round up to 2 because it is 0.5. And that's how many bacteria will be left after 8 days. And that about wraps it up for tonight's homework. Let me know if you guys have any questions on any of these problems or if you're struggling with the exponential growth and decay formulas. I'll be happy to help you out. But other than that, y'all have a great day, and I'll see you next time. Thanks for watching.